Monday is our last lecture.
That's right. I'll probably do numerical methods, which will take a super long time to prepare. Where are people? People should be here by now. This is unusual. But okay, sure, let's start anyway. So let's continue talking about central motion. So what we saw last time was that we had a proof that movement is confined to the plane. If you have an object moving in 3 dimensions that has a central force acting on it, well, we're now going to assume that we're working into a 2-dimensional system because we've shown that we can pass to a 2-dimensional system in which the object is moving. So I'm going to show conservation of angular momentum. And instead of defining what angular momentum is, I'll just do the proof. So suppose that we have coordinates r theta in polar coordinates. We have a force F is equal to FR of theta. And if we remember what the definitions of these were, then we had a coordinate system. And let's say you're located here. Then if there's some force that's acting on you, you can sort of break it up into these components, and you get a component associated with the radial part and the angular part. Well, if the force is acting centrally, that it's entirely radial, which means that F theta is equal to 0. What that means is that F theta is equal to 0, which is equal to mass times acceleration in the theta direction. But what is acceleration in the theta direction? At this point, we look back to the sort of really non-trivial results that we had in the last lecture. And we found that theta acceleration is 2r prime theta prime plus r theta prime prime. And so what we get as a result is this, we can divide by m, but we can also multiply by r. So we get as a consequence that's 2r r prime theta prime plus r squared theta prime prime is equal to 0. And by chain rule, or rather perhaps I shall write 0 is equal to this. This can be written as the derivative of some expression. What is that expression?
R squared theta prime.
Yep. And so as a corollary, what we get is that there's some value which we'll call h. R squared theta prime is equal to h, some constant. And h is the angular momentum. And okay, so what is angular momentum? Well, it is some quantity that is conserved in the course of the movement of a particle acting on being acted by a central force. And however, instead of motivating this, I'll show you how this theorem directly implies something that's sort of much easier to understand. And that's theorem 3. Equal areas are swept out in equal times. So the idea here is that suppose that you are moving and you have some section of a circle that's sort of uniform, and this angle is theta, and this radius is r. Then the area of this sector is equal to what's a circular sector. So it's going to be some fraction of the circle. What area does the circle have? It has area, pi r squared. And what area does, what fraction of the circle is relevant to this? The relevant fraction of the circle is theta over 2 pi. So the area is 1/2 pi r squared theta. Sorry, no pi, half r squared theta. So what we get then is sort of that the infinitesimal change in area. If we imagine that all of these are functions of time, let's write a prime. So if we just naively think that r and theta are both functions of time, let's see what happens. Because sort of you can then say that d A is half r squared d theta. But if we have that both r and theta are functions of time, then what's going to happen is that a prime is equal to half, or we would get rather, let's say r prime theta. Oh, I see. But right, so theta here is only meaningful as a change. So this really actually says sort of an infinitesimal change is equal to this infinitesimal change. It doesn't necessarily make sense to differentiate this expression. So what we'd have then is that given the equation that we have before, that's r squared a theta prime is equal to h. This implies that dA, or rather a prime, the time derivative of area, is equal to half r squared theta prime, which is equal to half h, this constant. So that tells us that area as a function of time, solving this differential equation, is half h t. But this means that area increases linearly. And that proves the result. Now, let's discuss force fields. So suppose that force fields. In general, if you have a force at every point, this is some function, vector valued function f of position, let's say. Then what we can do is we can also sort of consider this as well, we're going to consider the expression basically fx. So fx is a function of position. So consider fx dx plus fy dy plus fz dz as sort of a differential. We can ask if this is du for some scalar function u. This would mean and now we sort of have a bit of a confusing thing because sometimes I use this to denote partial derivatives, but here I'm using it to denote a component. So just to be consistent, I'll say partial u partial x is equal to fx partial u partial y So if there's a subscript on a vector valued function, then it refers to a component and not a partial derivative. Now, if such a function exists, then negative u is the potential of the field F. And the field is then known as conservative. Also, my headphones are about to die. So I will disconnect them and hopefully I can still hear people. And the idea behind a conservative field is that you sort of can't get energy from just moving in a conservative field. That there's a potential, and that's when you move, that's the energy change is the change in potential just from your position. So let's consider two examples. And the two examples you should think of are gravitational attraction and a spring. So imagine that you have like a spring pulling an object. Then what is the force spring proportional to? The force on the spring proportional to?
How much you stretch it.
Sorry, what was that?
The length of the how much you stretch it.
Yeah, so let's say F is equal to negative KR. And so this is like a spring. So what's going to happen is this gives a force at every single point. And the question is, does this force come from a potential? And so what we have then is if we wrote it in Cartesian coordinates, we'd have that fx. And the reason that I'm writing it in Cartesian coordinates is because this definition is sort of given in Cartesian coordinates, not in polar coordinates. And we'd have to consider a different one if we wanted to do that. It would not be a straightforward translation. So what fx is that it's going to be the cosine of the angle, which we can write from last time as x over r. That's the cosine of the angle that the direction forms with the x-axis. Which we can now just rewrite as negative kx. So the force in the x-axis they're sort of independent. It's just proportional to the displacement in x. And the force in y is just proportional to the displacement in y. Well, is there some function whose derivative is equal to these expressions? And so it's going to be a function u of x, y, and z. And we want the partial derivatives to equal these at every single point.
It would just be minus 1/2 kr squared.
So yeah, there's going to be a minus 1/2 K, and then what do I put here? In terms of X, Y, and Z, not in terms of R.
It would be x squared plus y squared plus z squared.
Yeah, that's good. And this can also be rewritten as negative K over 2R squared, because Pythagoras, right? So that's the potential associated with, well, rather that's sort of the force function. So the potential energy is actually the negative of this. The potential is K squared, or K over 2R squared. Now, example 2 is gravitational attraction. And how gravitational attraction works is that the further you are, the weaker the pull is, as opposed to this, where the further you are, the stronger the pull is. And so in gravitational attraction, you're going to have F is negative K over R squared, inverse square law. And so if we do the same thing, then we're going to have that Fx is K over R, sorry, X over R, negative K over R squared, which is going to give us negative K X over R cubed. And so the potential, or rather the negative of the potential, is equal to, so before, I guess, remember that R is so we have R is the square root of X squared plus Y squared plus Z squared. And sort of, if you take the derivative of this expression and by chain rule, you'd get this coming up front. The exponent here is basically negative 3/2, right? Of this. So if we add 1, then what do we get?
Minus 1/2.
Yes, so we probably want to put square root of X squared plus Y squared plus Z squared at the bottom. And then if we just differentiated this, then by chain rule, we get a negative out front, which is good. Then we'd get a 1/2, but then we'd also take the derivatives, and we'd have something like, if we were taking the X partial, 2X, and that would cancel with this half. So it would just be X. But there's a K here, so it's just this. Now, both of these potentials are only defined up to a constant, because we could have just as equally well written plus C here. But we're choosing not to write plus C. So potential energy is not uniquely defined. It's only defined relative as a difference between the potentials at 2 points. Notice that sort of the signs are different. So a potential is negative in negative U is the potential energy. So basically the best that you can have is that you're infinitely far away, and then your potential is 0. But if you are close to the objects, then your potential is negative. And so what that means is that you've gone from a high energy position, 0, to a low energy position, something below 0. which means that by, for example, falling closer to an object, you will have gained some energy from the energy lost in the potential, and that can be translated into kinetic energy. So this makes sense. Whereas in a spring, what happens is that negative potential is positive. So negative U, the potential is K over R squared. So the further you are away, the higher the potential energy you have is, which is sort of clear. It's the same as V4, except the exponent is different. Because here the exponent was at the bottom, so you'd max this out by making this infinity. Whereas here you'd max this out by making this infinity as well, except with signs, so it's in the opposite direction. And then if you're very far away, you have a lot of potential energy because the spring is really pulling you. And then if you get close, then this might go all the way to 0, which means that you have a lot of kinetic energy. So the theorem is in a conservative field, energy is conserved. And what energy means is sum of kinetic plus potential. So let's see how we prove this. Remember that the hypothesis is that we have that du is equal to fx dx plus fy dy plus fz dz. And if we consider something like that, well, f is ma. So we get as a result that sort of the partial derivative of u with respect to x is equal to m acceleration in the x direction. Now, what we're going to do is we're going to take this quantity and we're going to multiply it by dx. Battery. So the book does it in like a weird way, in a very engineering way, but I'm going to write mx prime prime dx dt. Plus my prime prime dy dt. Plus z prime prime dz dt is equal to, so basically I could write this as du dt. By chain rule. And by multivariable chain rule. And this is actually accurate. So a u is a scalar function. And the time derivative of u will actually equal this quantity by multivariable chain rule. So what we do is then, therefore, we integrate this. And if we're integrating this exactly looks like, well, x prime prime times the derivative of x. So if we were differentiating this, if we differentiated x prime, where x is a function No, what I wrote does not make sense. Well, the claim is going to be that if we integrate with this with respect to time, we have half m x prime squared. Oh, does this make sense? Yes, actually, this does make sense. Um, Suppose that I differentiated this expression. Then I get two x prime times x prime prime. Yeah, no, that's right. That's right. So yes, if I integrate this with respect to time, I get this expression. So I can write this as sort of mvx squared plus half mvy squared plus half mvz squared is equal to u plus some constant c. And remember that potential energy is defined as negative u. This implies that basically I could write this as half m absolute value of the norm of the vector v squared minus u is equal to c. Except for the fact that we shouldn't call it c, we should call it e, because that's the total energy of the system. And this is a constant. And that says that energy is a conserved function. So there's a quantity that we can associate with the motion that's energy when we've chosen a potential. Okay, now let's solve for the motion with the motion when, or maybe I should put a page break here. So let's suppose there's a force that's proportional to the distance. The question is, what sort of movement would we have? And the equations that we saw were that so we are going to actually use an interesting constant. We're going to say it's k squared m r. Because the object is going to have mass m. So this is a bit of a convenient constant to use. Then we have, for example, fx is equal to mx prime prime, which is equal to the x components of the force. So F times x over R. which we can then write as negative. We already basically did this with a different proportionality constants, x. Or rather, let's write my prime prime. Or sure. So what we can do now is that we get basically equations that are entirely decoupled. So we get x prime prime is equal to negative right. We are going to pass to a plane. We are going to assume that the movement is in the xy plane, because we've shown that it moves the xy plane. Okay, so we get the decoupled equations. X prime is equal to k squared x, and y prime prime is equal to negative k squared y. And these differential equations can be solved entirely independently of each other. So what we get is basically the characteristic equation lambda squared minus k squared plus k squared, which gives us roots plus or minus k I. And so the solutions that we'll get will be x is let's say c cosine k t plus d sine k t, and y is e cosine kt, and f, well, f is a bad letter to use. Let's call them A, B, C, D. Now, perhaps we'd like to solve for the movement for x in terms of y, because we'd actually like to know what equation this traces out, right? And so how we're going to do this is we're going to solve for cosine and sine. So we can think of this system as saying that A, B, C, D times cos kt sine kt is equal to xy. So as a consequence, we get that cosine of kt is equal to 1 over AD minus BC. Then D, that's not how you write a D. And hence 1, which is equal to cosine squared kt plus sine squared kt is equal to bx minus by squared plus minus cx plus ay squared divided by the discriminant squared. Now, if we want to write this out in terms of things, well, it's going to be the equation of an ellipse, not of a circle in general. Because if you just pull in one direction and it's at a steady state and you let it go, it's just going to travel in a line. But then if you sort of make it, if it's starts with a certain velocity in one direction, if you like throw it, then you can imagine that it's going to travel in an ellipse. So what we get as a result is that AD minus BC squared sort of plus, if we look at what's the term on x squared is going to be, it's going to be d squared plus c squared x squared. Then there's going to be a term on xy, and that's going to be negative 2. I guess this is negative if I've moved it to the side. And then here we're going to have b squared. And it's good that it's negative because it sort of has to counteract these terms. Plus a squared, y squared is equal to 0. Or alternatively, let's remove this negative sign. So that's a constant, and then this is sort of a quadratic thing. Except I can probably move this term over. Okay, this sort of, let's say that fits. And then the question is basically, if you have an equation of the form of, let's say, sort of like alpha x squared plus beta x y plus gamma y squared is equal to delta, then in general, this is going to be the equation of an ellipse. And how you can think about this is notice that this coefficient and this coefficient are both positive. So alpha and gamma are greater than 0. We have that. So basically what's going to happen is that alpha is going to try and complete the square with respect to something, and gamma is going to try and complete the square with respect to something. And we want those things to eat up this term while adding in a constant. So let's, I guess, I'm doing this pretty blind, try and basically complete the square here. Let's call this alpha squared plus gamma squared, because they are positive numbers. And maybe, okay. Then what we're going to have is that in order to complete the square, we'd have alpha x, and then we sort of want plus c squared that would have cross term alpha to alpha x c, and we want that to equal, oh, but it's beta xy. Okay, I do not know how to do my quadratic sections. So anyway, this gives you an ellipse. Long story short. But this gives the equation in terms of x and y, and then stuff. So sort of, let's do an example. So, or do I want to do this example or not? Sure, let's do an example. So let's say you have sort of, I'm just going to use the same numbers as the book. You have an object, and you have a force is, let's say, is equal to -1/8 r, and then you have a unit mass. And it's going to be moving, so it starts off moving like this with a velocity of 15 meters per second. Mass is 1 kilogram. Then what we have basically is the equation m x prime prime is equal to negative x over 8 and m y prime prime, except m is 1. So we can forget about m. And we have the initial conditions that I should also give sort of this distance. And let's say that this distance is 10 meters. Then what's going to happen is that 10 meters is a pretty big distance. This is sort of a very big spring. We have that x of 0 is equal to 10. Y of 0 is equal to 0. X prime of 0, it has no x components of motion. And y prime of 0 is equal to 15, right? So if we have the differential equation, the solutions that we'll see are sort of k here is 1/8. So it's I decided to make the mass different, is what happened. 2. Okay. 2x. So 16 is, on the other hand, a perfect square. So we're going to get that x is equal to c cosine 1/4 x, 1/4 t. Let's say AB. And then I think this is the first time that I'm actually doing this in the course. I'm going to plug some numbers in to get the initial conditions in. Then what happens is that if we differentiate these, we're going to get that x prime is equal to 1/4 a negative 1/4 a sine t plus 1/4 b cos t over 4. And y prime is negative 1/4 c sine t over 4 plus 1/4 b cosine t over 4. And now when we plug in the numbers, we're going to get, therefore, that, so let's call these equations 1, 2, 3, and 4. So from 1, we get that 10 is equal to, and then we're going to plug in time is equal to 0 here. And so 10 is equal to a is what we get from this equation. Then for 2, we're going to get 0 is equal to c. From 3, we're going to get that x prime is 0 is equal to 1/4 b. And from 4, we're going to get that 15 is equal to 1/4 d. So that tells us, and notice that in order to use these initial conditions, we actually did have to differentiate our equations. We would have been doing a lot more of this in almost any other differential equations course, but I avoided initial value problems a lot. So now we're seeing how to do them for the first time. So what we get is that x is equal to just 10 cosine t over 4. And that y is equal to so 15, 30, 60. But there's an easy way to solve these equations to give an equation in terms of x and y. So what's the relationship between x and y? Well, then we have that 1 is equal to x over 10 squared plus y over 60 squared. And that's clearly the equation of an ellipse, right? So it's the equation of a circle where we've squashed x and y by certain factors. So it gives an ellipse. Okay, and next we're going to do motion in a fields where we have inverse square law. But we should first take a break. So let's resume at 7:15. Okay, so for the next example, wait, how do I write this? I write motion when. So motion when force is going to equal, we're going to keep the mass inside of there just to make it nice. So this is going to be an inverse square law. So Km over r squared. Now, what's going to happen is this is again in the plane. By our theorem in reducing motion to the plane. And so if we were going to set up the equations as we did before, then we'd get x is x over r negative k m over r squared, which is going to give us negative k m x over r cubed. And the problem with this is that then we get equations that are of the form so that's equal to mass times acceleration. And so we get something like x prime prime is equal to negative k m over we canceled out mass kx over the square root, well, rather x squared plus y squared to the 3/2. And these equations are not decoupled, so we do not get decoupled equations. And so the approach that we did last time doesn't work. And it turns out that so this inverse square law, there's a lot more analysis to be done here than last time. Last time, it just happened that because we had these things precisely cancel out, we found that this formula f in terms of x prime prime, it was completely decoupled from y. But here we won't have that it's completely decoupled from y because the things don't cancel each other out nicely. So what we're going to do is instead we're going to do this analysis in polar coordinates. And that makes things possible. So what we're going to do is we have F is MA. Let's say the radial components of force is equal to mass times the radial components of acceleration. And what is the radial component of acceleration? So I'll save you from looking it up. It's going to be, I'm just going to write the equations. R prime prime minus R theta prime squared. And F theta is equal to M A theta is equal to M, and we already saw this equation before, 2R prime theta prime plus R theta prime prime. Now, as before, when we did the analysis of angular momentum, F theta is equal to 0 because central. So what this second equation yields is that there are some constants, and the analysis is going to depend on this constant, which is the angular momentum of the system. So the angular momentum of the system is h is r squared theta prime. So r squared theta prime is equal to h. And so this is going to be a constant in the solution. So the real reason that I did these equations last time was so that we could analyze the inverse square law, because we really do need these equations to do this analysis. So then what we get is that FR, on the other hand, well, we know what that magnitude is. It's just the full magnitude of the force. It's negative km over r squared. And yes, I did switch from a lowercase to an uppercase k here. Gravitational constants sort of look like that, while spring constants look like the other thing. So that's equal to mass times acceleration, radial. And what I can do is I have r theta prime squared. Well, sort of r squared theta prime is this. So I also get that theta prime as a consequence of this can be given in terms of r. It's this constant h over r squared. And so I'm going to plug that in here. And then I'm going to divide by r to the fourth. So I'll get r cubed. So I'll get h squared divided by r cubed. And then I have m. I'm going to cancel the m's out. And I'm going to multiply everything by r cubed. Or not. I'll rearrange it so that r prime prime is equal to, or other, sure. Let's just cancel the masses out for now. Cool. So it's good that we took the mass inside of this constant, because otherwise we'd have a mass term floating around and that would be annoying. So we just agreed to scale k by the mass, and then it's nice. Now, the thing is that this equation, there are ways to solve it. But we are going to not use the ways which are discussed later in the book. There's like special cases that you can do. Instead, we're going to do a really clever substitution. We are going to try and solve for r as a function of theta. So what we're going to do is we're first going to make a substitution. We're going to say that u is equal to 1 over r. Now, by the way, why am I using a lowercase u? Because if we go back to what we saw before with the inverse square fields, we saw that the potential energy was, this is, can also be written as, of course, k over r, right? So this is proportional to the potential energy of the system. So we're introducing the potential energy, although it needs to be scaled. So that's why I'm not writing capital U, but lowercase u. Now, what we're going to do is, first off, I'm going to write the engineering proof, or rather the physicist's proof. This is going to irk all mathematicians, but this is the way that physicists do it. So in undergrad, I was always sort of like driven against the wall by these things, but then I got used to them. But you're going to see that this is sort of amazing. So first off, here, this equation from before now tells us that theta prime is equal to h u squared, right? So r prime is equal to what? Well, r is 1 over u, where right now we're going to treat everything as a function of time. So if we do chain rule, we're going to get 1 over u squared du dt. Now, this is the step that I'm going to have to explain, and this is why I'm calling it a physicist proof. We're now going to imagine that u is a function of theta. So we're going to do chain rule and write du d theta, d theta dt. And we can do this because we're physicists. Well, d theta dt is equal to hu squared, right? But there's a u squared here, so that's equal to negative h du d theta. Now, let's say we want to find the second derivative of r. Well, then we look at this expression. And so you'd say, well, okay, this is a function. What's the time derivative of this? Well, the catch is that this is a function of theta, and you've differentiated it with respect to theta. So there's a chain rule. Now, is this clear that there should be a chain rule? Not at all. But physicists will know that because there's a theta here, u is now a function of theta. And so if you're differentiating by time, theta is a function of t, and so you get a chain rule application. So you're going to get negative h, and then sort of maybe we can write it as d squared u dt d theta, although this makes less sense than what I'm going to write. So I'll write it like this, d squared u, and now we're going to differentiate d theta squared. But here we want to take d dt. So we have to multiply by d theta dt in order to basically get our derivative with respect to u and then theta. Now, writing it as sort of du d theta, that's sort of nonsense because u isn't simultaneously a function of theta and t, it's one or the other. I'm going to explain what this means in a second. But if we look at this, then what do we know about h d theta dt? D theta dt is hu squared. So we're going to get negative h squared u squared d squared u d theta squared. So are you happy with this argument?
Pretty sketch.
Yeah, okay, so let's do the translation. I also think it's very sketch. So the translation is going to be this. We are going to assume an ansatz. And by the way, this is the argument that's written in the book. It is, yeah. So the ansatz is going to be that u is going to be, which is a function of time, can be written as u tilde, which is a function of theta of t. So this is actually an ansatz. that says that u can actually just be expressed as a function of theta, but theta is still a function of time, right? So then what's going to happen is that when we consider r prime, well, that's 1 over u, and this is a function of time. So we're still differentiating with respect to time. Now, if we think this means this is the derivative with respect to time of u tilde of theta of t. So what happens by chain rule is that we get negative, this is u squared. This is negative 1 over u squared d u tilde times its arguments, where its arguments by definition is going to be called theta. We're going to say that it's the derivative of this function, d theta, which is the name of the arguments. But what theta are we taking the value as? We're evaluating this derivative at theta t. And then we get by chain rule, d theta dt. And then we get the same line as before. D theta dt is h u. So this is negative h d u tilde d theta, the arguments evaluated at theta of t. So if you imagine u tilde as a function of some parameter, which we're going to call theta, then that parameter, which is sort of different from this theta is different from this theta. So maybe we can say u tilde is equal to u tilde of theta tilde. Although that might be confusing. In which case, or let's call it a blue theta. Let's just denote the difference between theta as a function of time and theta as the variable by letting that variable be blue. In which case, what's happening here is that we're differentiating with respect to the arguments of the function, which would be known as just theta. And so we have a blue theta here. So it's basically the derivative of this function with respect to its variable. So now we see basically that this theta and this theta, they mean different things, and this u tilde and that u tilde and that u, they mean different things. Whereas in the physicist arguments, you don't see that, right? But here, now we're able to make this rigorous with this ansatz. Now, when we take r prime prime, what we're doing is that this is a function of time only with respect to this dependence. So by chain rule, what we're going to get is we're going to differentiate this function again, but it's a composition of two functions. So it's going to be the second derivative of this function with respect to theta, the blue theta, the variable theta. And then we're going to keep the inside function. And then we're going to differentiate the inside function by chain rule. And then we get negative h squared u squared and d u tilde d squared u tilde d theta squared. Okay, is this less sketch now? Happy? Anyway, physicists do this all the time. In undergrad, I had to get used to this because I took a lot of physics classes. But sort of like, it's really not clear that this ansatz is being assumed. And it's really, you might naively not see that there's a chain rule here, whereas there actually is a chain rule because secretly this u is actually u tilde. Anyway, that is how physics works. Okay, so now what's going to happen is that, sure, we got these equations, and I'm going to go back to working in physics world. So U here denotes U tilde and U denotes this. Or maybe I can continue in math world for a while. Anyway, so what's going to happen is that I'm going to go back to an equation. I think it should still be copied. If I cut it and then undid it. So recall this. And so what we then get is that I'll write it in terms of U tilde. And then we're going to get minus H over now the thing is that we are writing everything in terms of U. So our equation is that U is 1 over R. So this is H squared U cubed. Oh, and then I should also probably say this is evaluated at theta of t. That's necessary in order to do the full math translation of this. It's this function evaluated the derivative with respect to its variable where we're taking the argument at this. And then negative equals negative k u squared. And so what's going to happen then is that if we divide by a u squared everywhere, and we're also going to divide by h squared everywhere, we're going to get d squared. I guess this is evaluated at theta of t. Okay, now we're going to write everything in terms of right? Then if we divide by h squared, well, negative h squared. We're going to bring this term over. Actually, no, we're not going to bring this term over. We divide by negative h squared, so we get plus u. But we're going to write this in terms of tilde. U is u tilde of theta of t, right? Is equal to a negative k over h squared, which are just numbers. U tilde squared theta t. Now abstract this. To replace theta of t with an arbitrary now theta is just going to denote some variable, not a function of t, with an arbitrary theta. So with an arbitrary, I should denote it by blue theta, because we're evaluating out theta of t at every point. So at an arbitrary theta that's no longer time dependent, what we're going to get is a first order differential equation with respect to u tilde. So this tells us that basically u tilde prime prime plus u tilde is equal to negative k over h squared. Sorry, we divided by u tilde squared. This is just a number. Right? And this is the first order differential equation for u prime. And I mean for u tilde. And it's not just a first order ODE, it's a first order linear. And we know how to solve this. So now we are going to be able to solve this. Sort of a second order. Now, for the homogeneous equation, what we get is that lambda squared plus 1 is equal to 0. So lambda is equal to plus or minus I. And how we are going to do this is that we're going to say that the solution, therefore, is u tilde, this is to the homogeneous part, is equal to, and we're, instead of writing it sine and cosine, we're going to write, let's say, some constant a times cosine of theta minus some offsets delta. So we showed last lecture or 2 lectures ago that we could combine sines and cosines to get this. Now, by the way, for the inhomogeneous equation, look at this. This is just a number, right? Let's say we use the ansatz. What ansatz are we going to use?
Homogeneous plus a linear term?
Well, we just want to, okay, fine. We could do separation of variables. However, let's do a super clever ansatz. Let's imagine that we were doing variation of parameters, right? So this is e to the power of 0 t, right? Or e to the power of 0 theta, rather, because everything is being expressed in this. So the ansatz that we use, because that's not a root of the polynomial, is some multiple of this exponential, right? So it's just a number. But look, if it's just a number, what's the second derivative of a number? 0. So then you just have that number, right? So actually, u tilde is equal to negative k over h squared solves the inhomogeneous problem. By inspection. And this is solution to homogeneous. So the general solution is u tilde is equal to a cosine theta minus delta minus k over h squared. Now we are going to rename these things. So what we're going to do is we are going to let a is equal to e, this is going to be called the eccentricity, times k over h squared. So then U tilde is equal to k over h squared. You know what? Negative this. Sorry, there's a thing. There was a thing. The thing is that in this equation, we divided by negative h squared. So in fact, this became positive. Or I didn't have to erase that. So then what we get is that u is equal to k over h squared. And then we get 1 plus e cosine theta minus delta. So this is u tilde as a function of theta, u tilde of theta. Maybe I can write. And maybe to make my conventions clear at this stage, I'll remind everyone that the theta is the variable theta, not the theta as a function of time. Although in particular, if we plug in theta equals theta t, then this is also going to be satisfied. Now, the book says that we basically get to choose our coordinate system. Choose coordinates such that delta is equal to 0. We're going to rotate all of the coordinates so that, in fact, u as a function of theta, we're going to measure theta differently, and then delta is going to be 0. So the thing is that we are going to get some particular solution from the integrating factors, and then in that particular solution, by rotating around, we get this. Basically, what does this mean? We're going to analyze this equation and show that it gives the equation of an ellipse. Now, without loss of generality, when doing this analysis, we can set delta equal to 0. Because sort of there's just a translation. Delta theta goes to theta minus delta that translates between one coordinate system and the other. So this isn't really that important of a remark. I'm just not going to have a minus delta floating around. Now, the goal is to show that this is the equation. And by the way, what I said before was false. I said we were going to show that this is an equation of an ellipse. So imagine that you have an object that's outside of the solar system. What does it mean for an object to be outside of the solar system? From outside to come into the solar system?
It would have to go into the sun. Oh, I mean,
not lit. It doesn't have to collide into the sun. So a long time ago, a few years ago, there was this interstellar object. I think it's the first one that we've ever detected. And it was really weird because it was very long. Yeah, so if I type in interstellar object, this is the first results. Let me just show you the Wikipedia page. So some people believe that this was sort of an alien device because it was very weird for an object that came from a thing. What it looked like, this is an artist's impression, is that it was very long and thin. So like incredibly cigar shaped, and it was like very big. And it's had a very unusual composition. And it also had some non-gravitational acceleration, but we could ignore the non-gravitational acceleration part. And it didn't look like a comet. It looked like a rocky object like this. And when we calculated the trajectory, we found that it was, so if you have like something like a comet is bound gravitationally to the sun, which means that it's going to travel around the sun and it's going to return periodically, right? the difference between a comet, which is always going to be bound to the sun and is going to have a maximum distance that it goes to the sun, is that an interstellar object is going to come in from a very far distance and it's eventually going to escape to infinity unless there are other gravitational influences from other solar systems. So that will not travel in an ellipse. That will travel in an escaping trajectory that escapes to infinity. So it's incorrect to say that in general, an object is going to travel in an ellipse, because you might have cases where it has high enough energy to escape to infinity. And so what's going to happen in general? It's not that it travels in an ellipse, but rather that it travels in a conic section. So what are conic sections? Well, you can imagine a cone. Right? And then imagine that we're going to take a plane through the origin and intersect it with this cone, right? So if the plane is sort of perfectly vertical, it's going to look like just two line segments, right? If you sort of intersect this with this plane, then you just get two line segments. So that's imagine that there's an object directly heading towards the sun. Sure. Okay. But now let's imagine sort of the other intersections that we could get. Wait, I don't necessarily want it to pass through the origin. I'm going to consider sort of general intersections. Okay, if I intersect a plane like this and it's perfectly flush, then I'm going to get a circle, right? But let's imagine that I do something interesting. Sort of planes through here, they're sort of not that interesting. You'll either get line segments or other things. So we want a general plane. Now, let's imagine that I instead sort of take an intersection that's like this. Well, then you can imagine that it's going to be a parabola. But if the plane is slightly tilted and it's not perfectly like that, and it's not the case that it wraps in, so if the angle is different from this angle, let's say this angle is bigger than this angle of the plane, then it's going to be a hyperbola. So the conic sections are, you can draw them as parabolas. So these are going to be prototypical examples. Y equals x squared, let's say a parabola. Then you can get ellipse, which includes the case of a circle. That's not a good ellipse. But I tried. Actually, that's not true. I didn't really try. Okay, now I'm trying it. Still not perfect, but whatever. Slightly better. Or you could get a hyperbola. And sort of the degenerate cases include a line, let's say. And so what happens in a hyperbola is that a parabola, if you take any line through the origin, it's going to intersect the parabola. I mean, not just at 0, but it's going to intersect it twice. It's going to intersect at 0, and then it's going to intersect again. Sort of, you can't make the line thin enough that it avoids the parabola because the slope here is 0, right? But in a hyperbola, it's different. In a hyperbola, there are sort of like two axes. And you sort of get asymptotic behavior where this stuff is hugging the axes, but it never exactly reaches it. And sort of the prototypical equation of an ellipse is x over a squared plus x over b squared is equal to 1. And the prototypical equation of a hyperbola is x over a squared minus x over b squared is equal to 1. And of course, all of these can be rotated around, made off center, translated in various ways. But these are what the conic sections look like. And sort of an ellipse is an intermediate case between a parabola is an intermediate case between a hyperbola and an ellipse. You can sort of imagine that's because here they're asymptotic lines, but here sort of stuff would anyway. It's not the case that it can be contained. So if you go from a point from here and you sort of, okay, anyway, I'm not doing a good job explaining the difference between a parabola and a hyperbola, but they are pretty different. Objects are basically in the solar system never going to travel on parabolas, because it'll turn out that a parabola is exactly the case when the parameter is a specific exact value. And if it's any more than that value, it's an ellipse. And if it's any bigger than that value, then it's a hyperbola. So you need to get exactly a real number, and there's no such thing as two real numbers agreeing in physics. So in reality, the orbit is either going to be an ellipse or hyperbola, but you can sort of imagine a degenerate case right on the boundary where it's a parabola. So the actual thing is that there's a cool definition of a conic section that does not apply to circles. And let's imagine that we have sort of a conic section. All of these roughly look circular-ish, right? Rather, I'm going to draw this line here. And then let's suppose that sort of the peak of the conic section is here. So if I draw it like this, then you sort of don't know what kind of conic section it is, really speaking. Now, there are going to be sort of 2 points associated with it. So this is a line of symmetry. There is going to be a point that's going to be called the focus. And there's going to be a line somewhere else that's perpendicular to this axis called the directrix. And what's going to happen is that in every single conic section, except for the circle is the case where the directrix moves to infinity, as I'll explain later. What's going to happen is that for any point P on the conic, we can consider drawing a line from the focus to P. And then we can consider dropping a perpendicular to the directrix. And what's going to happen, that does not look very perpendicular. That's a bit better. What's going to happen is that we're going to get 2 distances. Let's call this distance R, and let's call this distance D. And the definition of a conic section, apart from a circle, is that it is defined by a focus and a directrix and a certain ratio that R and D have. So R over D is constants. Is constants. And that ratio is known as the eccentricity of the conic section. So it used to be the case that, like, I guess 30 or 40 years ago, when people studied in high school, they taught them like Euclid's, and they also taught them Newton's Principia. And when you looked at those books, they sort of really emphasize conic sections, So this book, it says, for example, it talks about the solar systems, and then it talks about Halley's comets. And then it mentions that, for example, let's see, the comments is sort of, where is it? Anyway, oh, here it is. The famous Halley's Comet has an elliptical orbit whose eccentricity is 0.967. Its period is 76 years. Its perigee is 0.587 astronomical units. And then it mentions what an astronomical unit is. Since it last visited us in 1910, it will be visible again in 1986. And 1986 was sort of like the distant future from when this book was written. But that's a long time ago. That's way before I was born. Anyway, so you will, I'm sure that everyone here has seen sort of other definitions of what the conics are, because an ellipse sort of has two focuses. And then the usual definition of an ellipse is that if you take a piece of string and you sort of add this distance to this distance, then that sum is constant. That's the usual definition of an ellipse. And sort of the degenerate case of an ellipse is when both focuses converge to one, in which case you can just imagine a piece of string doubled, and then that's a circle. In a hyperbola, the usual definition is slightly different. It's that I think in a parabola, it's sort of the directrix definition. That's the usual definition of a parabola. But in a hyperbola, it's if you take the ratio of two quantities. So a hyperbola has a certain focus, and then it has the origin, which is a directrix. And what it says is that the difference of these values is constants. So that's the usual definition of a hyperbola. Don't 100% quote me on this, but I think it's the difference of these. Anyway, both of these are special cases of this definition, which also works for a parabola. In a parabola, it's there's also a focus, and it's that's anyway. So the definitions fall out. So what's going to happen is that sort of this distance right here, by the way, is called the perigee. Perigee, not perigee, of the conic section. And sort of there's this is transverse. Anyway, let's see what happens. So basically, what we have is we can take this focus and then we can drop a perpendicular upwards. And if this is an ellipse, well, it wouldn't be tangents. Let's call this point Q. And let's call this distance D1. And this is called the semifocal width. So we're doing a lot of conic section trivia today. Anyway, what we're going to do is that this is going to be some value. And we're just going to choose to call this value h squared over k, which is what we had sort of here, but there's the reciprocal of it. So suppose that we have a conic section where the semifocal width is h squared over k. Then what can we say about the values that we'll have? Let's figure out what the equation of the conic is going to be. So the equation of the conic is going to be that the eccentricity is equal to r over d, right? By definition. But it's also equal to It's true at P, but it's also true at the point Q prime. And at the point Q prime, we have this semifocal width of h squared. That's R over KD1. And this only, we're going to assume that h does not equal to 0. So there is angular momentum. When h equals 0, when there's no angular momentum, can you imagine how an object would be moving? Well, it would be a degenerate ellipse where you have some speed, but then you can't escape to infinity, really, because actually you can escape to infinity. There is an escape velocity if you're just traveling transverse. But you'd either oscillate in a line passing through the sun, you collide with the sun, but imagine that you could pass through it. Or maybe if your speed is quick enough and you achieve escape velocity, you can escape the solar system and just extend the line to infinity. But we can also see from the figure that suppose that this angle is theta. Then what we have is that this is r cos theta. So we also have that d1, which is this distance, is equal to r cos theta plus d at any point on the ellipse, right? So what we get then is that this implies that d1 is equal to h squared over k. Well, I guess we divide by e. So what we get is that h squared over ke is equal to, then we have also that if we just rearrange this equation, that r is equal to ed. So r is going to equal ed cos theta. Rather, actually, we want to keep r. What do we want to keep? We want to keep no, r cos theta, I'm happy with r. I want to replace d with r over e. Because here we replace d, here we're also going to replace d. So we're going to get r over e plus r cos theta. And so what's going to happen then is when we rearrange this equation, what we're going to get is we can factor an r out. Well, okay, let's do it step by step. So let's multiply everything by e. So we have h squared over k is equal to r factored out 1 plus e cos theta, right? So that's a good sign. And rearranging that, we get that r is equal to h squared over k. This is a capital K. I didn't draw it as a very capital K in all of these instances. It was looked capital here, but then here it stopped looking capital. Well, I guess 1 over 1 plus e cos theta. And that was the equation that we saw. Well, that was the equation for u, right? But what is u? U is by definition 1 over r, right? so I guess that implies that R tilde, which is the function of theta, R tilde of theta is equal to, so 1 over R, we get R here, we get H squared over K, and then we get 1 over E cosine theta. And then we're working in the system where we make delta 0. I guess I can sort of write it in minus delta if you want. Later on, it goes away. So what we've discovered is that by this definition of a conic section, which was a bit of trivia, but all of these are cases of it, we find that a conic section has the equation that we found. So basically setting these values to be arbitrary things, if we set the semifocal width to H squared over K, then we also have the eccentricity, and sort of that specifies a bunch of stuff. Now, can we do? Well, sort of, you imagine that if you know what the eccentricity is and you know what the semifocal width is, then you also know what D1 is. So you know how far this line away is. And then once you plot this line as being this far away, you know where the pedigree is because you want this ratio to be a specific thing, right? So what's the anatomy of a conic section? So E is going to, first off, it's going to be a non-negative number because it's defined as a ratio of two quantities. E is less than 1 implies elliptic. E is equal to 1 implies parabolic. And E is greater than 1 implies a hyperbolic. And the degenerate case of E is less than 1 E is equal to 0 is the case of a circle. Now, looking at this equation, why is it obvious that E equals 0 is the equation of a circle?
Because then it's, that other thing goes away, and it's 1 over 1, and then it's constant.
Yeah, so it's a number. It says the radius is a number, so it's a circle. So you're staying on a circle. Good. So this is clear why it's a circle, right? But for the other values, and then if we think about it, the eccentricity is defined as the ratio of R over D. So what would it mean to have a ratio of R over D equal to 0? Well, R is always going to be something, so it's really, we're setting D equals to infinity. So sort of if you imagine moving the directrix away as we go to infinity, you'd converge from, I guess if you want to keep a fixed semifocal width, let's keep the semifocal width fixed. And imagine then as we move the directrix away, we're changing D1 and that changes the ratio. So if we make this be very close, then we're going to have sort of elliptic orbits. Then at a certain point, it's going to become parabolic when this ratio is 1. But then when the ratio is less than 1, it's going to be elliptic. And sort of if you move the line all the way to infinity, then the degenerate case is that of a circle. So that's how it works. Okay. I think that let's take a 7-minute break, and I'm going to do a bit. No, why not take a 10-minute break? Resume at 8:25. I think a break is good. And then we can do a bit more. Hopefully this conic section trivia was fun. But you can see that the analysis here was a lot more complex than a spring. We actually found that planets move in conic section orbits, and that required the equations that we did before. But cool. So planets, movement, conic sections. Anyway, see you soon. Okay, it looks like, yeah. So this is sort of a classic differential equations problem. And I guess I can tell you what the problem is called, which is a spoiler to the solution. This will be called the, where is the word? Catenary problem. What is going on? Is there a button that's being pressed? Okay, that was weird. Oh, I probably maybe held down. Okay, that stylus glitch. Okay. And so imagine that you sort of have a cable that's held between 2 points. So imagine that you hold a piece of string, right? So let's imagine that you have a string of a certain length. The length is going to be fixed, right? And let's say you hold the string. Well, the string is basically going to drape down, right? And if you hold a piece of string, it'll assume this shape. What shape does it assume? Isn't that a good question? And similarly, let's imagine that you have bridges that sort of have suspension cables on them. Although that's the suspension cables are sort of supporting the bridge. So that's a bit of a degenerate case. Now, by the way, if you hold the string like this and like this, and the string is sort of short, well, if the string is just flush, then it's going to be a straight line, right? And there's going to be no horizontal tangents. But if you just extend it by a little bit, it's going to look like this. And sort of how you can imagine that is if you took this one and you imagined putting another point here and you cut the string into two, then both of those parts would stay in the same shape, right? And so if you cut it here, you'd see this in general. So how are we going to model this as a differential equation? Well, the idea is that the string has a certain length and then it has a weight. The reason that it's drooping down is because gravity is acting on it. So it has a certain weight per unit length. So it has, let's say, a linear density. Let's say W is the linear density. You know what? That's a silly. I'll call it lambda. That's a much better name for a linear density than W. W looks like a total weight. So segments of length, and I'll write differential. D S weighs. Let's write sort of like dW is equal to lambda ds. Right, cool. Let's say that also this is going to be weight in terms of not linear density, but linear density divided by the constant of gravity. We divide or multiply. So we multiply by G to get a force. Okay, now we are going to do sort of an infinitesimal analysis. We're going to imagine that sort of a lot of stuff in this piece is constant. So imagine that you sort of have a piece that looks like this in general. I guess I drew it well last time, so I'm going to copy that over. And what's going to happen is that there are going to be two tangents. There's going to be a tangent to the curve here, and we can call this direction T1. And there's going to be a tangent to the curve here. Let's say this is the tangents to the curve here. And notice that in general, they may have been bets across this. So the tangent here and the tangent here are actually going to be different. And then what we can say is that let's imagine sort of drawing y-axis parallels. So this is going to have angle theta1, and this is going to have angle theta. Now, the forces acting on the system, assuming that it's sort of all infinitesimal on this segment, there's going to be a tension here, and it's going to be acting in the opposite direction. Sort of, the actual tension is in the opposite direction. This is the tangent direction, but the force is in the opposite direction. And then there's going to be a weight that's going to be acting on the center of mass of this object. And I can maybe draw that in red, or it's a force, so it's going to be in green. It's going to be directed downwards, and that's going to be the force of gravity. So it would be mg, where really we've already multiplied by g. So it's going to be lambda ds. That's a number, but it's directed downwards. So what's going to happen is that these three forces have to balance out. So you can imagine that this is an infinitesimal part of the cable, maybe between these 2 points. These three forces have to cancel out no matter how small we make this, and then we're going to get a differential equation when we take the limits. So then we're going to do a component analysis. We're going to do sum of forces acting in the x-axis and sum of forces acting in the y-axis, right? So this one, by the way, is going to act in this direction. So I guess maybe I can instead draw this in red, because that's where we're measuring the angle from. But in green, I can actually draw the direction of the force as going here. And I'm not sure that the way the book is presenting it, which is the way that I'm presenting it, is necessarily the best way to present this problem. But anyway, in the x-axis, the forces, so the object isn't moving, so the net sum of forces has to be 0. Then we're going to have a T1. And then if we want to look at the x component, it would be sine theta1 minus t sine theta. And in the y-axis, gravity acts. So what we're going to get, well, we're going to have the weight term. So this is acting negatively. So it's going to be, this is also acting negatively, T1 cosine theta 1 minus T cosine theta minus lambda del s is equal to 0. Now we can sort of imagine taking this discrepancy of t cos theta across the endpoints. We can write that maybe another way to write this is that the change in the quantity t cos theta is equal to T1 okay, so basically we get, okay, we can write it like this. If we just refer to this quantity as del t cos theta, then delta of t cos theta is equal to 0. Sorry, delta t sine theta is equal to 0. Sorry, am I bad? I am, this is along the x-axis. I don't know the difference between my cosines and sines. Yeah, the opposite of this. So del t cos theta is equal to 0, and del t sine theta is equal to lambda del s. And how we can think about this is then we can say, well, let's imagine the change with respect to x. So if that's going to say that d dx, let's imagine that these are functions of x. Now, the first equation is going to tell us that t cos theta is some constant, h, right? And so what we can do is we can take the second equation and we can divide both sides by h. So then we get that d dx of on this side, we're going to divide by t cos theta, and it's a constant, so it can come inside of the derivative. And we're just going to refer to this as k ds dx, because these are not going to get separated later. So let's just remember that k is equal to lambda over h. And we can solve for these later on. So but let's think about what tan theta is. Tan theta is exactly this rise over this run, which is going to be the slope of the curve. So tan theta at a given point is going to equal dy dx, right? So what we get as a result then is that let's also think about what ds is. Ds is equal to the square root of dx squared plus dy squared. So infinitesimally, if we imagine the change in length, it's we can forget about the fact that it's curved because we're in a very tiny space. And so what that tells us is that ds dx is equal to, this is sort of the formula for arc length, 1 plus y prime squared. So overall, what we get is that d dx of tan theta, which is yx, so d t d squared y dx squared. Oh, but it's t over t, so that goes away. Good. Is equal to k square root 1 plus dy dx. I'll write it like this. Now, that equation is a nonlinear equation. However, what we're going to do is we're going to reduce it to a first order equation, and then we're going to do some cleverness. So in order to reduce it to an equation, we'll let u equal y prime. In order to reduce it to a system. Then the equations that we get are that u so u prime is yes, so that says that dy dx is equal to u, and then this equation becomes dy squared, so that's actually du dx. So y and u are functions of x, is equal to k square root 1 plus u squared. And that reduces it to a linear system. But it's a non-linear system because we have 1 plus u squared, so that's a bit annoying. However, what we can do is this equation, it's independent of y, right? So we can solve this. So what that tells us is that u is equal to the k times the integral of the square root of 1 plus u squared. This is going to be no. Yeah, okay, so yeah, do we multiply by dx? So u is a function of no, we are okay, where this is anyway. Yeah, no. How do I solve this? Separation of variables. Okay. Du. So k dt is equal to du over square root 1 plus u squared. Now, if we sort of do this integral, it's actually not going to be arcsine. It's not. What we're going to do is arcsine would be a bit different. Okay, no, I still have to finish this. I'm going to make the substitution. So if I sort of take square root 1 plus u squared and I differentiate this, then I'm going to get the 2's canceling out. It's going to be u divided by square root 1 plus u squared, right? But now if I think about it, if I let's w is equal to square root 1 plus u squared, then what is u equal to in terms of w?
Square root w squared minus 1.
Yeah, it appears that this substitution might be less helpful than I thought. Okay, well, integrals are hard. You could do trig substitutions here. That would also work. But let me just sanity check and do the thing that I don't want you to do and look up this integral online. Which I'm not going to teach you how to do, if you don't already know. So 1 plus x squared to the 1. Right, but how do I? Okay, fine. They just say that it's a hyperbolic sign. But no, that's not how I want to do it. I actually want to do a solution. Yeah,
Maybe if
this just go ahead.
I mean, like, since hyperbolic sign is defined in terms of e to the x and e to the negative x, like, is there something you could do there, like for the substitute?
That's a good point. You know what? I want to finish this example. So let's just do this. Consider the function logarithm of u plus square root 1 plus u squared. There's always a way of calculating integrals by taking derivatives, isn't there? So if we differentiate this, what we're going to get is by chain rule, 1 over u plus square root 1 plus u squared. And then up top, we're going to get, this is with respect to u. U. And then here we're going to get, so 1/2 plus, so that's going to cancel. And then we're going to get u over square root 1 plus u squared. Okay, now let's try and rearrange this. So we're going to multiply top and bottom by the conjugate of this equation. So we're going to multiply by u minus square root 1 plus u squared. And what we get as a result is that the denominator becomes u squared minus 1 plus u squared, right? And what does the top become? Well, we're going to get u squared. Then we're going to get this cross term, minus u square root 1 plus u squared. Then we're going to get this cross term, which is plus u squared divided by square root 1 plus u squared. And then we're going to get minus u. So overall, this becomes minus 1. And then what we want to show is that this is the square root of 1 plus u squared. So let's bring everything to, wait, is this actually? Are you sure about this book? Okay. Anyway, algebra time. So at least the denominator clears up. So u squared square root 1 plus u squared. Let's write it like that. It would really be nice if this were a u squared, wouldn't it? Okay, let's assume that this works out for a second. Okay, anyway, you do some calculation and you get that y is dots, dots, dots. Not a good last actual solving example. That u is equal to 1/2 e to the k x minus x naught. And these are going to be integrating factor, minus e times e to the negative k x minus x naught. There are actually some tricky manipulations here. And this can also be known as the hyperbolic sign of k x minus x naught. And that's the equation of a floating thing. And then you could do some analysis on it, and you could figure out sort of what h is, because you can work backwards through some stuff. Now I want to figure out this integral. I have 6 minutes. I'm going to figure out this integral. So first off, what is going on here? Okay, if we bring things to a common denominator, negative over square root 1 plus u squared, which is what we ideally want to have, we get u squared square root 1 plus u squared. Then we get negative u times 1 plus u squared. Then this is plus u squared, and this is minus u times square root 1 plus u squared. So it would all cancel out if this u were a u squared, is what it seems like. This final answer is correct. But I'm not going to be able to fix this now. You know what? I'm going to work this out now, and then I'm going to send you the notes with the corrected calculation. There has to be a nice way to do this integral. Okay, what I plan to do on Monday is I plan to write a lot of code this weekend, and hopefully, if I have time, I can do a lesson on numerical methods. You know, I will actually, I will finish this example at the start of next time. So let's erase all of this and actually do this example properly, because it's unsatisfying to not do it properly. Okay, see you on Monday, which will be our last lecture, and then I'll send you the videos soon. Have a good night. Bye.